chair this session on polymers, ceramics, composite materials, and nanomaterials. We have seven. Thank you. We have 7 presentations. The first one is by Lowe. You have 15 minutes to present the paper and discussion at the end of the session.
Just a second. Yes, does it works? Okay. Yes, thank you for the introducing words. And welcome to my presentation, a mixed mode controlled DCB test on adhesive joints loaded in a combination of modes 1 and 3. I structured the presentation that I will give you a short motivation. Then I will go on with the load case, and based on this load case I will explain the test setup and the manner of test control. And after that I will explain or show you some results of the MCDCB test, which is the mixed mode 1+3 performed test. And some of the results I will compare to results of the mixed mode 1+2 test. And I will close this presentation by a summary. So I will start with the motivation. Well, if we are thinking about mode mixity, we are often thinking about the mode mixity under mode 1+2. And a large number of test configurations are well established to investigate these mixed mode behavior under mixed mode 1+2. So one of these tests, for example, is the mixed mode bending, the MMB test, where the specimen is loaded with uneven bending moments at the upper and lower adherent. So one of the problem or the disadvantage of this test is that that we cannot realize any arbitrary mode mixity. So as you can see here in the figure, both modes, mode 1 and mode 2, acting in one plane. So mode 1 is affected on mode 2 and mode 2 is affected on mode 1. So they both are coupled. And if we now have a look at the here performed test, we are loading the specimen in mode 1 and mode 3. So both modes are acting in orthogonically arranged planes. So therefore we can realize an individual mode mixity. Furthermore, the test which we propose here holds even for nonlinear elastic fracture mechanics. In contrast, the MMB test holds only for linear elastic fracture mechanics. So this was the motivation. Then I will go on with the load case. First of all, we have used a modified double cantilever beam DCB specimen. And this DCB specimen you can see here, we loaded this specimen at the end of lever arm with an actual moment denoted here with my, to evoking the pure mode 3 separation or pure mode 3 loading. And with the actual force here denoted with Fy, we are introducing or superimposing additional mode 1 loading. So as I mentioned before, with this load case, we are able to realize any arbitrary mode mixity. So if we now have a look at the boundary conditions and imagine that we are separating the specimen out of plane as well as in mode 1 direction, there will be further moments or external loadings occur at the boundary of the specimen. So if we now have a look regarding the evaluation of energy release rate using the J integral, we have to consider all these external loadings acting on the boundary of the specimen. So with this equation, we can determine the energy release rate using the J integral, and thereby the first two summands are the intended, or we call it intended contributions, and denote this contribution which corresponds to mode 1 as well as to mode 3 separation or loading. We call these loadings J1 and J3. Furthermore, there are two further contributions, and these contributions are something like a mode 1 plus mode 2 separation or loading, and this one is something like a mode 1 separation out of the plane. So these two contributions we denote as artificial or unintended contributions. And we have to be ensured that these contributions must be in a negligible order of magnitude. So if this statement is fulfilled, we can define the mixed mode ratio, here defined with chi, in terms of J3 and J1. So then I will go on with the test setup and the manner of test control. The tests have been performed into a biaxial tension torsional testing machine, where the specimen is clamped into an upper and lower clamping device, where the lower clamping device constrains all rotational degrees of freedom, but enables a free movement in plane, so we can avoid several lateral forces acted at the end of the specimen. And so if we now rotate the upper clamping device around the blue-colored axis, we can evoke the pure mode 3 separation. And if we then superimpose axial displacement into along the blue-colored line, we can superimpose the mode 1 separation. Furthermore, the crack opening displacement, or the components of crack opening displacement, the COD, is measured by an optical measurement system using digital image correlation, and the local angle theta has been measured or detected by an incremental shaft encoder, and several forces and moments are detected by a multi-axial load cell. So with this test setup, we are enabled to measure the contributions of J, J3 and J1 during the test procedure. And furthermore, the charm of the testing machine is that we can control the axial as well as the rotational axis on external Z points. So if we determine, for example, the J3 component contribution, and predefining any arbitrary mode mixed ratio chi, we can generate the J1 Z point. So all in all, we can say that the test can be controlled on contributions of J, in this case J3 and J1. So therefore, we are calling this test the mixed mode controlled, or MC-DCB test. The test conditions are that we have been used 29 specimens with a constant as well as variable mode mix ratio. We have applied a structural adhesive Sieger Power 498, which is a crash optimized adhesive. We have used a nominal adhesive layer thickness of 0.3 millimeters. And the test conditions are that we applied quasi-static test velocities. Okay, then I will go on with some results of these MC-DCB test. And I will start with the artificial contributions. And just for remind, we have divided J into 4 sumens, where the first 2 sumens are the intended contributions, and the last 2 sumens are the unintended artificial contributions. And these contributions must be in a negligible order of magnitude. So if we now have a look at the figure below, we can see that the percentage of artificial contributions with respect to J1 and J3 is plotted over J, whereby J is normalized by its maximum J max. So what can we see is that approximately 5% of J max, the percentage of artificial contributions is equal or even lower than 5%. And furthermore, this figure represents the mixed mode ratio, constant mixed mode ratio under 0 degrees, which equals a pure mode 1 loading. So if we now have a look at further mixed mode ratios between 0 degrees and 19 degrees, whereby 19 degrees equals the pure mode 3 separation, we can see that when we are using this threshold at approximately 5% of J max, we can see that the percentage of artificial contributions is at each mixed mode ratio distinctly or significantly lower than 5%. So we can state that above 5% of J max, the artificial contributions are in a negligible order of magnitude. Okay, then I will go on with the critical energy release rate. So this is the energy release rate which we have determined from the intended contributions, J1 and J3. And what we can see here is in the figure is that we have plotted the energy release rate versus the mode mixed ratios. And as I mentioned before, 0 degrees pure mode 1, 19 degrees pure mode 3, and approximately between 0 and 60 degrees, we can see that the critical energy release rate is nearly constant in this region. Approximately at 80–85% or above, then the critical energy release rate rises distinctly. So if we now have a look at the figure on the right side, there the energy release rate J3 is plotted over the energy release rate J1. And in the figure on the left side, the black dots depict the critical energy release rate of constant mode mix ratio, while the blue lines depict the energy release rate of variable mode mix ratio. And what we can see is that both test types are corresponding in a good agreement. Furthermore, and that is quite a nice add-on, these continuous blue lines show us the shape of the fracture envelope. Okay, then I will compare some of these results with results of a mixed mode 1+2 test. Here I will compare the MNC DCB test with a CMMB test, which is quite a small extended version of the well-known MMB test. And the difference between the CMMB and MMB test is only that this CMMB test is controlled of components of crack opening displacement. So if we now have a look at the figure below, you can see that the black dots, which represent the MCDCB test results, and the red dots, which represent the MMB test, are in a good agreement and correlate to each other. So therefore, we can figure out that we can reproduce with the MCDCB test the test results of a mixed mode 1+2 test. But with the MCDCB test, we are able to, or this test holds even in case of nonlinear elastic fracture mechanics. So we can use this test, for example, to investigate hyperelastic adhesives. So furthermore, with this MCDCB test, we can realize any arbitrary mode mix ratios. So for example, we can load the specimen under mode 1 with pressure and introducing or superimposing a mode 3 separation or something like that. Okay, then I will summarize. We have a new fracture mechanical test under mixed mode 1+3 proposed. This test was controlled on contributions of energy release rate. We have checked the artificial contributions and have seen that above 5% of Jmax, we can neglect the artificial contributions. And furthermore, we have evaluated the fracture envelope with constant and variable mode mixities. And at least we have compared the results of the MMB test with results of the MCDCB test and have seen that both results are correlating. And yes, so this work has been supported by the Deutsche Forschungsgemeinschaft, and thank you for your attention.
Thank you for your nice presentation. We have time for a very short questions or comments, please. Just a moment.
Oh, thank you for the very nice presentation. Did you compare the mode 3 to the mode 2 value for fracture resistance?
Yes.
And how do they compare?
Compared the EMF test to the 3 test, and they compare in a good agreement. So we have as
So outer plane is very similar to in-plane fracture resistance. Okay.
Competitors rather the traction separation also.
Yeah.
As fast as we publish with the guys from Bristol
Yeah.
in 2011, and they did it perfectly.
Okay.
The wandering thing, it was expected to rise, and
Yeah.
no friction, I don't think
Yeah.
caused by friction,
Yeah.
but here we definitely have no friction,
Yeah.
because the galvan force to zero
Yeah, yeah.
expected to be caused by plasticity or something like that.
Yeah.